In this video, I am going to discuss about the Schwarz lemma. It is one of the most important lemmas appearing in complex analysis. First, I would state the lemma. Suppose you have some analytic function from unit disk to unit disk. Okay, so and this analytic function maps 0 to 0. Okay, so this is important. Then these two conditions are held. The modulus of fz is less than or equal to modulus of z for any z in the unit disk, and the derivative of this function at 0 is bounded by 1. Okay, so right. So actually, we know that the derivative evaluated at 0 is the uh, first Taylor coefficient. So, for example, if you write the Taylor series expansion of fz around 0, you would get something like this: fz equals a naught plus a1z plus a2 z square, like that. So actually this is the derivative. Okay, so that means the Taylor coefficient a1 is bounded by 1. That's what the condition B says. Okay, then the next condition is interesting. So suppose you have some point z naught. Okay, suppose you have some point z naught inside this unit disk such that the modulus of fz naught is equal to modulus of z naught. Okay, then the function fz is a rotation. Okay, so if you input z, you would get z e to the I theta. That means the complex number z is rotated by an angle theta. Okay, if this condition happens, or if the derivative at 0 is equal to 1, then fz is rotation. Okay, that means if either of these two conditions are going to be held, then the function is a rotation. Okay, I hope you got an idea of the Schwarz lemma. Right, so let's move into the proof of the Schwarz lemma. Right, so I know that f is an analytic function. I have the function f from the unit disk to unit disk is analytic, and I know that this function maps 0 to 0. Okay, so what I have to prove, if z modulus of fz is less than or equal to modulus of z, and I have to prove that the derivative of the function of f evaluated at 0, its modulus is bounded by 1. Okay, right. So let's focus on part A first. Okay, right. So I would draw the unit disk again. This is my x-axis, y-axis. This is my unit disk. And this is the origin. Okay, right. What I'm going to do first is I would pick some simple r in between 0 and 1. Okay, pick simple r such that r is in between 0, 1, 0 and 1. Okay, so then consider the disk whose center is 0 and radius is simple r. Okay, so that means we are going to consider some disk like this, and its radius is simple r. Okay, right. So now I'm going to define another function gz. Okay, gz, and I would define gz in this. Gz is fz divided by z if z is not equal to 0, and gz equal to f dash 0 if is at d equals 0. Okay, so now you can see that the function g has a removable singularity at z equals 0, and g0, so g0 and g0 is not infinity, right? Because if you plug 0 to this function, you would get f dash 0. So gz has a removable singularity at z equals 0. And what is g0? G0 is limit z goes to 0 fz over z. Okay, so this is equal to f dash 0. Okay, all right. So from this we can say that so gz is analytic in D. Okay, so the function gz is analytic in the unit disk. Okay, now previously I defined a disk whose center is simple R. Now what I'm going to do is I'm going to evaluate the function gz on the boundary of the disk that I defined. Okay, right. So let's consider on the boundary what would happen to gz. Gz. So since gz is an analytic function, we know that it attains its maximum value on the boundary if it is analytic on the boundary. Okay, so we know that gz is analytic in the closure of this bound. Hence, it attains its maximum on its boundary. That means da by b0r. Okay, right. So what is the value of gz on the boundary? So how do we define gz on the boundary? So actually I need the value of gz on the boundary of this disk. What can you say about gz? So on the boundary z is not equal to 0. So this is how I am going to define gz. Okay, right. It is equal to modulus of fz divided by modulus of z. And I know that fz is bounded by 1 because f is an analytic function from the unit disk to unit disk. So this is less than or equal to 1 divided by z. And I know that on the boundary, modulus of z is equal to r. So this is equal to 1 divided by r. Okay, right. So this is an interesting point of our proof. Right, so you know that on the boundary of the disk that I defined, the modulus of gz is bounded by 1 over simple r. Okay, now what can you do to this disk that I defined? So you can pick any simple r that is in between 0 and 1. So what I'm going to do next is I would send the limit of simple r to 1. Let send r to 1 from its left side. Okay, right. So then what can you say? Then you can say that gz is less than or equal to 1 on d. Okay, because now R is approaching to 1, so that means we are getting closer and closer to the boundary of the unit disk. So therefore we can say that on the unit disk, the absolute value or modulus of Gz is bounded by 1. Okay, right. Okay, so from this, what can we say? If Z equals 0, what do I have? I have G0 modulus less than or equal to 1. So what is G0? It is F dash 0. I have the result that says that F dash 0 modulus less than or equal to 1. This is the first result that I need. Okay, let's try to get the next result. So this is part B. So I proved part B first. So let's prove the part A. Right, so in part A, what we need to show, the modulus of fz is less than or equal to modulus of z, but I know that this holds when z equals 0. Okay, since if 0 equals 0, this holds when z equals 0. So if I can prove this result for z non-zero case, then I'm done. Okay, so but it's very easy because we know that when z is not equal to 0, what is the absolute or modulus value of gz? It is defined as the fz over z, okay, which is the modulus of fz divided by modulus of z, and we proved that the modulus of gz is less than or equal to 1 for any z in the unit disk. So I can say that the modulus of fz divided by modulus of z also less than or equal to 1. Okay. Right. So now what do I have? From this, I can say that fz less than or equal to modulus of z. I have the result that I need. Okay, right. So I proved the first portion of the lemma. Okay. Now next condition is, next we are going to apply another condition. So next we suppose that there exists some z naught that is not equal to 0 in B or in unit disk, such that if z naught modulus is equal to z naught modulus. Okay. So what do I have then? If I divide it by the modulus of z naught, it would get 1, but this is equal to g of z naught. Okay, right. So what has happened? The function g has attained its maxima at a point different from the boundary, or in other words, if an analytic function attains its maximum at a different point in the boundary, or if an analytic function attains its maxima at some point in the domain, then it should be a constant function. Okay, so what has happened? I have the unit disk. This is the unit disk. So I have point z naught somewhere there, and G is attaining the maxima at this point z naught. Okay, Gz attains its maxima at Z equal to Z naught, that is in D. So, by the maximum modulus principle, what do we have? Maximum modulus principle, Gz, modulus of Gz is constant. Okay, right. So, what can I say? What is modulus of Gz? We know that when Z is not equal to 0, modulus of Gz is equal to modulus of Fz over modulus of Z, and this is equal to some positive constant k. Okay, right. So, but what is this constant? We know that at Z naught Gz equals 1, so this constant is going to be equal to 1 because at Z naught the modulus of Gz is 1, so it should be 1 everywhere in the domain. Okay, so I have this result. If Z is equal to modulus of Z, okay, when Z is not equal to 0, but we know that at Z equals 0, both of them are 0, so this holds for any Z in the unit disk. Okay, right. So now what can I say about Fz? Now I have two complex numbers and I know that their modulus are equal. So what does this mean? Fz is Z times e to the I theta for some theta in 0 to 2 pi. Okay, right. So okay. Now I assume that there exists some Z naught such that this condition holds. Okay. Now let's consider the second case. Next we suppose that if that 0 is less than or equal to 1, that means modulus of, next suppose the modulus of f dash 0 is less than or equal to 1. Now what is modulus of f dash 0? So this is equal to G0 is equal to 1, right? Yeah. I have to assume modulus of f dash 0 equal 1, but by the definition of Gz, I know that modulus of f dash 0 is equal to G0. Okay, right. So what has happened? G of 0 is equal to 1. Modulus of G of 0 is equal to 1. Alright, so again, what has happened in this case? I have the function Gz that is analytic in the unit disk, and its modulus attains its maximum value at the origin, and the maximum value is equal to 1. So what can I say? G attains its maxima at Z equals 0. So again, by the maximum modulus principle, by maximum modulus principle, what do I have? The absolute value of Gz should be less than or equal to 1. Okay, right, because G attains its maximum at the origin, so its modulus should be equal by the maximum modulus principle. It should be the same constant everywhere else. Okay, because that's what maximum modulus principle says. Okay, so that means in this case my analytic function g attains its maxima at the origin, so its modulus should be a constant throughout the domain, so it should be equal to 1. Okay, right. So again, I do not need to worry about the z equals 0 case because I know that f0 equals 0. So what I'm going to do is I would consider z not equal to 0. If z is not equal to 0, what is gz? It is the modulus of fz divided by the modulus of z is equal to 1. And I have this equality. Okay. So uh, what can I say? As I did in the previous part, if z equals to z e to the I theta for some theta in 0 to 2 pi. Okay, so and note that this holds for z equals 0 because if 0 is equal to 0. Okay, right. So I hope uh, you understood what I did here. So actually, the proof follows from the maximum modulus principle. That's the interesting part of the proof. Okay, so again, I would roughly go through the steps that I did. So what did I do? So first I selected some disk that is contained in the unit disk and its radius was simple r, and the function that I defined gz was analytic in the unit disk, so it attains its maxima in the boundary of this disk. Okay, so I proved that on the boundary the modulus of gz less than or equal to 1 over r. So again, I have not written that step. By maximum modulus principle, the absolute or modulus value of gz is less than or equal to 1 over r for every z in the disk that I define. Okay, right. So then I send the limit of r to 1. Then what did I get? The modulus of gz less than or equal 1 on the unit disk. Then I considered the z equals 0 case. Then I directly get the result that the derivative of the function f, the modulus of the derivative of my analytic function evaluated at 0 is bounded by 1. Okay, and then I considered this a non-zero case and I got the next result. Okay, then I moved into the equality case. Okay, that means first I assumed that there exists some z naught such that the modulus of f z naught is equal to modulus of z naught, and I proved that if z is a rotation, then I assume that the modulus of the derivative of the function f evaluated at 0 is equal to 1. And by using that, I proved again that f is a rotation. Okay, right. So I hope it's clear what I did. So if you have any questions, you can mention them in the comment section. Thank you for watching.